Hi kids! Today's lecture is about gas laws. We are going to be focusing on the properties of gases and their various relationships to each other. The first two properties of a gas we're going to compare are the pressure and volume. This is known as Boyle's law. Let's watch this video. Syringe with marshmallow inside. The part of the syringe that you can push up and down is called the plunger. Plunger can move up and down to change the space inside. I am putting my finger over the opening to trap air inside. No extra air can get in and none can escape. Watch what happens to the marshmallow when I push the plunger down and pull it back, all while the air is trapped inside. When I push the plunger down, the marshmallow gets smaller. When I pull the plunger back, the marshmallow gets bigger. It goes back to its normal size when air can get in and out again. The first three questions go together. When you push the plunger in, is the volume increasing or decreasing? Correct, it's decreasing. The gas inside the syringe is taking up less space. Question 2. When you push the plunger in, is the pressure increasing or decreasing? Well, as the gas occupies less space, the pressure now increases, and we prove that by question 3 with regards to what happened to the marshmallow. When the plunger was pushed in, the marshmallow got smaller. That's because the pressure of the gas inside the syringe was increasing since its volume was decreasing, and therefore creating a greater force on the marshmallow, pushing at it, pushing at it, pushing at it, and forcing its size to get smaller. Questions 4, 5, and 6 go together. Let's look at them. When you pull the plunger out, is the volume increasing or decreasing? Correct, it's increasing. There's more space now for the gas to occupy. When you pull the plunger out, is the pressure increasing or decreasing? Well, they being the gas particles, now have more space with which to move, so the pressure is going to decrease, and that was evident based upon what happened to the marshmallow. When the plunger was pulled out, the marshmallow got bigger. This is because there's now less pressure pushing on the marshmallow and its size is able to expand. In conclusion, what is the relationship between pressure and volume? Is it direct or indirect? Well, let's look at the questions. We said that number 1, volume was decreasing. As a result, the pressure was increasing. Notice that these two properties are moving in opposite directions. When that happens, the relationship is referred to as indirect. Conversely, in numbers 4 and 5, when volume increased, the pressure decreased. This can be mathematically related and is known as Boyle's law. Boyle's law says that the pressure times the volume of a gas under one condition will be equal to the pressure times the volume of that gas under a second condition. So the subscripts 1 and 2 are describing conditions 1 and 2. And that is true when we're at the same or constant temperature. just like we were in our little syringe marshmallow demonstration. Let's move to the next relationship. This time we're going to look at the volume and temperature of a gas and see how they're related. We'll watch this second video. Any ads that play on YouTube are not necessarily supporting the opinion or beliefs of your teacher. They are simply ads from YouTube.
Go Walk in Skechers Go Walk 5, our most advanced walking shoe yet. We deliver technology in every step, featuring impact-reducing Skechers Comfort Pillars, air-cooled Yoga Mat insoles, and a shoe that's now machine washable. We made the best better. Skechers Go Walk 5.
We made the best better.
Today on Sci Guys, Can Crush. Today on Sci Guys, Can Crush. Welcome to Sci Guys. I'm Ryan.
I'm Adam. On today's episode, we're going to be crushing cans using air pressure.
I want to crush something.
On today's episode, we're going to be crushing cans using air pressure.
I want to crush something.
Supposed to be open.
Supposed to be. Yeah, I guess you're right.
Open. Air pressure is the amount of force that gas particles exert on their container or environment.
Air pressure is the amount of force that gas particles.
The equipment and ingredients you're going to need for this episode include
an empty can,
a large bowl,
a set of tongs,
some water,
and a stovetop.
Because we're dealing with boiling water today, the safety equipment we're going to need include goggles, heat-resistant gloves, and an apron or lab coat to protect from spills or splashes.
The first step in our experiment is to take some cold water and fill up our bowl. The
second step of our experiment is to pour about 100 milliliters of water into the can. Turn your stove to medium-high heat and place your can with the water in it in the center of the burner. Leave it there until you see water vapor coming out of the top. Now quickly dunk your can into the water.
Let's look at this experiment a little closer. Before we heat our can, it's filled with liquid water and gaseous air molecules. Heating our can adds energy to our liquid water. The more energy we give our water molecules, the more excited they get, and the further apart the molecules spread. Once enough energy has been added to our liquid water, it changes state from a liquid to a gas. This gas is called water vapor. As our water vapor fills our can, it presses against the sides of our can, creating an increase in pressure. When we place our hot can upside down in our cold water, all the water vapor molecules that fill our can get really close together and turn into a few drops of liquid water. This liquid takes up a lot less space than a gas. Water in its liquid state doesn't exert nearly as much pressure on the inside of the can as it did in its gaseous state. At this point in our experiment, the outside atmospheric pressure is much higher than the pressure inside the can. In nature, pressures want to be balanced or in equilibrium. This imbalance causes the can to violently collapse, creating a balance between the pressure inside and outside of the can. This violent collapse toward the center of the can is called an implosion.
Well, that's it for Can Crushes. I hope you enjoyed it.
If you did, drop us a like and a comment below and subscribe for future episodes.
Like us on Facebook and follow us on Twitter.
And if you have any questions related to this episode or about science in general, let us know in the comments below or message us on Facebook and we'll try to help you out as best possible.
Thanks for watching.
Bye!
Ryan got to crush.
Thanks for watching. Bye! Ryan got to crush.
To the best of your ability, draw a sketch of the can while it was heating on the stove. To the best of your ability, sketch the can after it was immersed in the cold water. Question number 1. How did the temperature of the gas change in the can? Well, we went from heating on the stove into cold water, so the temperature decreased. Number 2, what happened to the volume of the can when you placed it in the cold water? The volume decreased. The can crushed. Number 3, what is the relationship between volume and temperature? Is it direct or indirect? Well, let's explore it a little bit. As the temperature decreases, what happens to the volume? As temperature decreases, which is what happened in our lab, we went from hot to cold. What happens to the volume? Well, we said in number 2, the volume decreased. The can crushed. Temperature and volume are both properties that are changing the same way. In this example, they're both decreasing. That's an example of a direct relationship. So the temperature and the volume of a gas are directly related. They change the same way. So 3b, as temperature increases, what happens to the volume? As temperature increases, the volume, because it's a direct relationship, must also increase. And maybe some of you have seen that in your everyday life. If you've ever been at a party or at a dance where there are helium-filled balloons, and you let one of them go and they rise and they land at one of the lights on the ceiling, eventually that balloon's going to pop because the heat being given off from the lights is heating the temperature of the gas inside the balloon. And if the temperature goes up, the volume or the amount of space that that gas wants to occupy is also going to go up. So it's going to expand, 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 and eventually the rubber will stretch and the balloon will pop. This relationship is known as Charles' law. Charles' law, and we can express it mathematically in this fashion. Volume 1 divided by temperature 1 is equal to volume 2 over temperature 2. And again, subscripts 1 and subscripts 2 are meant to imply condition 1 and condition 2. For example, on the stove versus in the cold water bath. Or balloon resting on the table and then balloon up by the lamp or the light bulb at the ceiling. That's what we mean by condition 1 and condition 2. Let's look at another relationship, the pressure and temperature of a gas. Let's watch this video. Gay-Lussac's law, the relationship between pressure and temperature when the number of moles and the volume are kept constant.
We're going to put the Gay-Lussac's device into a boiling water bath.
We're going to put the Gay-Lussac's
We'll wait a
device
few
into a
minutes so
boiling
that the
water
gas
bath.
inside the sphere
We'll wait a few
reaches the
minutes
same
so that the
temperature
gas
as the
inside
bath.
the
We
sphere
will then read the
reaches the same temperature
of the
as
water
the bath.
and
We will
the
then read the
pressure
temperature
off the
of
gauge.
the water bath and the pressure
The temperature
off the
is
gauge.
100.0 degrees Celsius.
The temperature is
Pressure
100.0
is
degrees Celsius. The pressure
948 millimeters
is
of mercury.
948
We now have a bath
millimeters
which
of
is a
mercury.
mixture of boiling water and
We now
room
have a
temperature
bath
water.
which is a mixture of boiling water and room temperature water.
Temperature is 51.5 degrees
The
Celsius.
temperature is 51.5
The
degrees
pressure
Celsius.
is 838 millimeters of mercury.
The pressure is
We
838
will now put the
millimeters of mercury.
Gay-Lussac's device in a bath of
We will
room
now put the
temperature
Gay-Lussac's
water.
device in a bath of room temperature water.
The temperature is 24.0 degrees Celsius.
The temperature is
The pressure is
24.0 degrees
770
Celsius.
millimeters of mercury.
The pressure is
We will now
770
put
millimeters
the
of mercury.
Gay-Lussac's device in a mixture of
We will
ice
now
and
put
water.
the Gay-Lussac's device in a mixture of ice and
After
water.
a few minutes, the temperature is 0.0
After a
degrees
few minutes,
Celsius.
the
pressure
temperature is
is
0.0
715
degrees
millimeters of
Celsius.
mercury.
The pressure is 715
Now we will put the
millimeters of
Gay-Lussac's
mercury.
device into liquid nitrogen.
Now we will put the
We will
Gay-Lussac's
not
device
use a mercury
into
thermometer
liquid
to record
nitrogen.
the temperature
We
since
will not
mercury
use a
freezes
mercury
at
thermometer
minus
to
33
record the
degrees
temperature,
Celsius.
since mercury
We will
freezes
rely on the
at minus
fact that the
33
liquid
degrees
nitrogen will be
Celsius.
at its boiling point,
We will rely on the
which is
fact that
minus
the liquid nitrogen will
197
be at its
degrees
boiling
Celsius.
point, which is minus 197 degrees
The
Celsius.
pressure is 230 millimeters of mercury.
The pressure is 230 millimeters of mercury.
Before we enter that data into our data table, I do want to come back to our Charles law information and specify, just like they did at the beginning of our lab that we just watched, that this relationship is true when our gas is under a constant pressure. So Charles law relationship is true when we're at a constant pressure. Again, the video we watched of the soda can on the stove and the soda can in the water bath, it's at the same pressure, atmospheric pressure. Those two conditions were at the same room. All right, so getting back to our Gay-Lussac's law, our data table. In the first trial, we worked with boiling water, whose temperature is 100.0 degrees Celsius. The pressure of that was 948 millimeters of mercury. In the second trial, the mixture of boiling water and room temperature water, our temperature was 51.5 degrees Celsius, and the corresponding pressure was 838 millimeters of mercury. Trial number 3 dealt with room temperature, which was 24.0 for that particular room on that particular day, and the corresponding pressure was 770 millimeters of mercury. Our fourth trial was freezing, 0.0 degrees Celsius, and the corresponding pressure, 715 millimeters of mercury. And finally, the liquid nitrogen, negative 197 degrees Celsius, and the corresponding pressure, 230 millimeters of mercury. Analyzing this data, what is the relationship between pressure and temperature? Is it direct or indirect? Well, what's happening to our temperature? We started at 100 degrees Celsius and we went all the way to negative 197. So that would be this second scenario here. As temperature decreased, what happens to the pressure? As temperature decreased, let's look at our pressure data. 948 millimeters of mercury, all the way down to 230. That also is decreasing. Pressure is decreasing. When both of our properties or variables change the same way, that is referred to as a direct relationship. So temperature and pressure have a direct relationship. Knowing that, we can answer 1A. As the temperature increases, what happens to the pressure? Since they're directly related, they both have to change the same way. As temperature increases, pressure increases. How can we show that mathematically? Gay-Lussac's law says P1 divided by T1 is equal to P2 divided by T2. Again, the 1 and the 2 represent condition 1 and condition 2, and this is true when our gas is at a constant volume. That's why the device that was used in the laboratory experiment was this like a tank. It was a hardened, sealed container device made out of metal. It was not going to expand or contract. Its volume, or the amount of space that the gas occupied, was constant. And again, the 1 and the 2 represent condition 1 and condition 2. If you were listening to the videos very carefully, the soda can demonstration, the Sci guys were going to talk about the volume and pressure of a gas. All three of these relationships, pressure volume, volume temperature, pressure temperature, they can all be related at the same time. They're all interchangeable. So these three variables can be combined into what is known as the combined gas law. We would write that as V1 times P1 over T1 equals V2 times P2 over T2. And again, these are one gas under two conditions. On the stove, off of the stove. Base of a mountain, top of a mountain. We're analyzing the same gas, though, under two conditions. In the freezer, out of the freezer. We'll work with the math together in class. We're getting the concepts down right now. And all of these concepts, or these relationships between the volume, pressure, and temperature of a gas come from what's referred to as the kinetic molecular theory. This is a theory that chemists use to describe the behavior of gases. And these theories, or postulates that make up the theory, are assumed by all chemists to happen every time we talk about a gas. Let's watch the video, and if you're able to split screen, great. If not, we'll write the postulates down together afterwards. The kinetic molecular theory. Again, disclaimer, the ads are not necessarily approved or endorsed by your teacher.
Grammarly does more than catch errors. With Grammarly, you can find really good. No.
With Grammarly, you can find really good.
Let's learn about kinetic molecular theory.
Professor Dave here. Let's learn about kinetic molecular theory. He knows all about the science stuff, Professor
We have learned about different laws that can be applied to ideal gases.
We have learned about different laws that can be applied to ideal gases.
Are merely
Like any
summaries
laws,
of
these
observations,
ideal gas laws
such as the way
are merely
pressure and
summaries
volume
of
are
observations,
inversely proportional,
such as the way
or
pressure
the way
and
volume
volume
and
are
temperature
inversely
directly
proportional, or the way
We
volume and
observe these
temperature are
relationships
directly
to
proportional.
always be true.
We
But
observe
again,
these
just like
relationships
any other
to
law,
always
it
be
does
true.
not explain
But again,
why.
just like
For
any
that,
other
we are
law,
going to
it
need
does not
something more
explain
powerful.
why.
We need
For
a
that, we
theory.
are going to need something
And the theory
more
that
powerful.
explains the
We
behavior
need
of
a
gases
theory.
is called
And the
kinetic
theory that
molecular
explains
theory.
the behavior of gases is called
This theory
kinetic
consists
molecular
of 5
theory.
postulates, and from them
This
all
theory
of the
consists
ideal gas
of
laws
5
can be
postulates.
derived.
And
So
from
let's
them,
go through
all of the
each
ideal gas
postulate
laws can
and
be
talk
derived.
about what
So
they
let's
mean.
go through each postulate
Number 1,
and talk about
we make
what
the
they
assumption
mean.
that a gas is made up
Number
of
1,
particles,
we make
whether
the
they are
assumption that a
individual
gas
atoms
is made
or
up of
small
particles,
molecules,
whether
and
they are
that these
individual
particles are
atoms or
always
small
in motion.
molecules, and that these
Throughout their
particles
motion,
are always
these
in
particles
motion.
travel in straight
Throughout
lines,
their motion,
unless
these particles
they collide
travel
with something,
in straight
whether
lines,
that is another
unless
gas
they
particle
collide with
or
something,
the walls
whether
of
that
whatever
is another
container
gas
they are
particle
in,
or
at
the
which
walls
point
of
they will
whatever
bounce
container
off
they
and
are
change
in.
direction.
At which point they will bounce
This
off
vision
and
of gas
change
particles
direction.
as moving around like billiard
This
balls
vision
on a
of
pool
gas
table
particles as moving
seems pretty
around like
intuitive,
billiard balls
but
on a pool table
it is an important
seems
one,
pretty
as it
intuitive.
implies that
But
tiny particles,
it is an
like
important
atoms,
one, as it
are
implies
subject
that
to
tiny
laws of
particles,
motion,
like
just
atoms,
like
are
macroscopic
subject
objects
to
are,
laws of motion,
and that they won't
just
just
like
stop in their
macroscopic
tracks
objects
and
are,
change direction
and that they
without
won't
cause.
just stop in their tracks
Number
and
2,
change direction
we can
without
assume
cause.
under most sets of conditions
Number 2,
that the gas
we can
is
assume
mostly
under
empty
most
space.
sets of conditions
This means
that the
the
gas is
fraction of the
mostly
total
empty
volume
space.
that is occupied
This
by
means
the
that the
particles
fraction
of
of the
gas
total volume
themselves
that is
so
occupied
close
by
to
the
zero
particles of
that we
gas
simply
themselves
ignore it,
is so
regarding
close
them
to
as
zero
essentially
that we simply
dimensionless
ignore
points.
it, regarding them
This
as
is in
essentially
stark
dimensionless
contrast
points.
with solids and liquids,
This
which
is in
are
stark contrast
non-compressible,
with solids
because
and liquids,
all the particles
which are
pretty much
non-compressible,
right up against one
because
another.
all the
There is
particles
very
are
little
pretty much
empty
right
space
up against one
between
another.
the particles.
There is very little
Number
empty
3,
space
the
between
phenomenon
the
we
particles.
refer to as pressure
Number
is
3,
actually
the
the gas
phenomenon we
particles
refer
in
to
the
as
sample
pressure is
imparting
actually the
some
gas
of their kinetic
particles
energy
in the
of
sample
motion onto the
imparting
walls
some of
of
their
the container
kinetic energy of
every
motion
time they collide with
onto the walls
just
of the
like
container
a macroscopic
every time they
object
collide with it.
would transfer energy
Just like a
onto some
macroscopic
surface
object
during a
would
collision.
transfer energy onto
It may
some
seem
surface
like atoms
during
are
a
so
collision.
tiny that they can't
It
impart
may
much
seem
force.
like atoms
and
are
that's
so
true.
tiny that
but
they
remember
can't
that in
impart
any
much
sample
force.
of gas,
And that's
there
true.
are trillions
But remember
and
that in any
quadrillions
sample
of
of gas,
particles.
there are
So
trillions
altogether,
and
it can add up
quadrillions
to a
of
lot.
particles. So altogether,
If there are a
it can
lot of
add up to
particles
a lot.
moving very fast,
If
there
there
are many
a lot
collisions.
of particles moving
so
very
the system
fast,
has a lot
there are
of
many
pressure.
collisions.
If there
So
are
the
very
system
few
has a
particles
lot of
moving
pressure.
very slowly,
If there are very
few
few particles
collisions,
moving
and
very
thus
slowly,
the system
there
has
are
very
very
low
few
pressure.
collisions, and thus
Number
the
4,
system has
we
very
ignore the
low
possibility
pressure.
that gas particles
Number
could
4,
exert any
we ignore
kind
the
of
possibility
gravitational
that gas
or
particles could exert
electromagnetic
any
influence
kind of
on one another.
gravitational or electromagnetic
Although they
influence
technically
on one
can
another.
interact slightly
Although
due to
they
dispersion
technically can
interactions
interact
or
slightly
even
due to
dipole-dipole
dispersion interactions
if the
or
molecules
even
are polar,
dipole-dipole
we consider
interactions
such
if the
interactions
molecules are
to
polar.
be entirely
We
negligible.
consider such
so any
interactions
collision will
to
be
be
purely
entirely
elastic,
negligible.
or
So
occurring
any collision
with no
will
loss
be purely
of kinetic
elastic,
energy.
or
They will
occurring
simply
with
bounce
no
off
loss
of one
of
another.
kinetic energy.
Once again,
They will
like
simply
balls
bounce
on a
off
pool
of
table.
one another. Once again,
And
like
number
balls
5,
on a pool
the
table.
average kinetic energy of
And
the particles
number
in
5,
the gas
the
is
average kinetic
proportional
energy
to the
of the
temperature
particles
of the
in the
gas
gas
in Kelvin.
is proportional to
This
the
means
temperature
that
of the
if
gas
you
in
increase
Kelvin.
the temperature, you
This
increase
means that
the
if you
kinetic
increase
energy,
the temperature,
which means
you
the
increase
particles will
the
be
kinetic
moving
energy,
faster.
which means
This
the
means that
particles
in
will
this
be moving
specific
faster.
context,
This
temperature
means
is
that in
entirely
this specific
indicative
context,
of average
temperature
molecular
is
velocity.
entirely indicative
So
of
those are the
average
5
molecular
postulates
velocity.
of kinetic molecular theory.
So those are the
These
5
postulates
postulates
are
of kinetic
powerful
molecular
in
theory.
explaining the
These
behavior of
postulates
gases.
are
And to
powerful
see how,
in explaining the
let's quickly
behavior
review
of
our
gases.
understanding
And to
of
see
some
how,
of the
let's
ideal
quickly
gas
review
laws.
our understanding
For
of
Boyle's
some of
law,
the ideal
we can
gas
see that
laws.
if we keep temperature constant,
For Boyle's law,
meaning the
we can
molecules
see that if
move
we
at
keep
the same
temperature
speed,
constant, meaning the
increasing
molecules
volume
move
must
at the same
decrease
speed,
the pressure.
increasing
because
the volume
particles
must
have to move
decrease the
farther
pressure.
to reach the
Because
sides.
the particles have
and
to move
decreasing
farther
the volume
to reach the sides.
must then increase
And
the pressure.
decreasing the volume
This is why
must
pressure
then
and
increase
volume
the pressure.
are inversely
This is why
proportional.
pressure and volume are
For Charles's
inversely
law,
proportional.
if we increase the temperature,
For Charles's
in order
law,
to keep
if we
pressure
increase
constant,
the temperature,
meaning the
in order to
frequency
keep
of
pressure
collisions
constant,
stays the same,
meaning the frequency
volume
of
must
collisions
expand.
stays the same,
because if
the
the particles
volume
move
must
faster,
expand.
but also
Because
move farther,
if the particles
they will
move
hit
faster,
the sides with
but
the
also
same
move
frequency
farther,
as before.
they will hit the sides
This is why
with the same
volume and
frequency as
temperature
before.
are directly proportional.
This is why volume and temperature
Looking
are
at
directly
Amundsen's law,
proportional.
we can see that increasing
Looking at
the temperature
Amundsen's law,
while
we can
keeping
see
the
that
volume
increasing
constant,
the temperature
the
while
pressure
keeping the
must
volume
increase
constant,
as the
the
particles
pressure
are moving
must
faster.
increase as
This is
the
why
particles
pressure
are
and
moving
temperature
faster.
are directly
This is why
proportional.
pressure and temperature
All
are
of these laws,
directly
which are
proportional.
simply statements of
All of
observation,
these laws, which
now
are
make
simply
perfect sense
statements
in the
of
context
observation,
of kinetic
now
molecular
make
theory.
perfect sense in the
Thanks for watching,
context
guys.
of
Subscribe
kinetic
to my channel for
molecular
more
theory.
tutorials. Support me
Thanks
on
for
Patreon
watching, guys.
so I can keep
Subscribe
making
to my
content.
channel for more
And
tutorials.
as always, feel
Support
free
me
to
on
email
Patreon so I can
Professor
keep
Dave
making
Explains
content.
at gmail.com.
And as always, feel free to email me, ProfessorDaveExplains@gmail.com.
All right. Thank you. Friendly reminder, this kinetic molecular theory describes an ideal gas. The kinetic molecular theory describes an ideal gas. Just like you may have this perfect image of the ideal person that you want to be, in a relationship with, they don't really exist. You're going to have some things on your list that you ignore or overlook because there's no such thing as the ideal person. The same thing is true in chemistry. There's no such thing as an ideal gas. However, we have this list of how gases are supposed to behave. Real gases can behave like ideal gases, though, when they're under the conditions of low pressure and high temperature. And we have these conditions because, remember, real gases, like the gentleman on the video said, they are going to have forces of attraction where their instantaneous dipoles or the polarity of their molecule are going to have them interact with each other. But if those real gases are under low pressure, meaning there's nothing forcing those gases, particles close together, and they're under high temperature, meaning they have enough energy to move far apart from each other, they are going to best behave like an ideal gas and therefore meet these postulates of the kinetic molecular theory. So the first postulate stated that particles are in constant rapid random motion. Constant rapid random motion. The particles travel in straight lines. Until they collide. Where they'll bounce off each other. As a result of bouncing off, they change direction. Postulate number 2 said that a gas is mostly empty space. The particles are so small, their volume is insignificant. Postulate number 3. The pressure of a gas is the force exerted on the side of a container. When you talk about the pressure, it's resulting from the force, or it's being measured, exerted on the sides of the container due to the collisions. Postulate number 4 gets back to what we were talking about earlier. The particles have no interaction with each other. Particles have no interaction with each other. Again, this is an assumption for an ideal gas. And then finally, the last one says that our average kinetic energy of the particles is going to be directly proportional to the temperature. And the YouTuber was kind enough to tell us that this has to be in what's called the Kelvin temperature scale. And let's elaborate on why. And the video did not go into this. The Kelvin temperature scale has this thing called absolute zero. We also need to remind ourselves that kinetic energy is the energy of motion. So if I'm speaking for a car, for example, and it's has no motion, its speed is 0 miles per hour. When I'm talking about 0 degrees Celsius, for example, or 0 Fahrenheit, both of which are temperatures that we're able to reach in our everyday lives, the particles are still moving. There are still colder temperatures. In Fahrenheit and Celsius, there are negative temperature values. Well, if the value of 0 is meant to be no motion, that's what's meant by absolute 0. Particles have no motion. At absolute 0, the particles have no motion. And absolute 0 is the value 0 Kelvin. 0 degrees in Fahrenheit and 0 degrees in Celsius, our particles still have motion. So in Fahrenheit and Celsius, they are not a direct measurement of the kinetic energy of our motion. The only temperature scale where 0 means no motion is our Kelvin temperature scale. So every time we're talking about a gas, we have to convert into Kelvin. And the reason why we have to convert is because none of our thermometers directly measure in the Kelvin temperature scale. Our thermometers in the laboratory measure in degrees Celsius. So we have to convert the data that we get from lab into the Kelvin scale. And we do that by adding the value 273 to it. If you wanted to look in a textbook, it would be 273.15, but we don't need to be that specific. Another way to phrase this fifth postulate of the kinetic molecular theory is that every time we're talking about temperature, we're doing so in the Kelvin temperature scale because that's the only one where 0 means no motion. And if temperature is going to represent the kinetic energy, which is the kinetic energy or energy of motion, then the only temperature scale we can use to directly measure motion is the Kelvin temperature scale. Finally, there are 5 vocabulary words that describe a gas in various situations. Please pause the video and take a minute to match each picture to its correct vocabulary word. The vocabulary words are diffusion, effusion, compressibility, expansion, low density, and fluidity. If you need to look up what these words mean on the sciencedictionary.com link in our Google Classroom, please feel free to do so. Welcome back. Let's check our answers. Well, looking at these pictures in no particular order, I'm going to start here in the lower left corner. And I see this scientist looking at a gas, and it's moving as if it were a fluid. This picture is describing fluidity. Although it's not always easy to see because the majority of our gases in our world are invisible to our human eye, the gas particles do have the ability to roll and flow over each other and act like a fluid. The next picture I'm going to look at is the top middle. These hot air balloons rising in our atmosphere, that's describing the property of low density of a gas, right? Things with low density float. Gases have the least density of our states of matter, and that's what causes them to float or rise. Low density. The next one I'm going to do is the bottom right. As I look at this before, during, and after, the during, the wall, or the amount of space that my gas was able to occupy increased, and after, the particles filled or expanded to fill the space. This is representing expansion. Three words left, 3 pictures left. I'll now focus in on the top left. This reminds me of that syringe I was looking at before. How I can move it in and out to compress a gas. This is showing us that a gas is mostly empty space, which allows the gaseous state of matter to be compressible. I can apply a pressure and force those particles to move closer together, filling in the gaps of the empty spaces. Our last 2 vocabulary words, diffusion and effusion, you probably needed to look up the words, and the difference is effusion is describing a gas escaping through a pinhole-sized opening. And this picture in the upper right corner, the teeny tiny holes in the latex rubber balloon, is describing the effusion. And if you've ever blown up a latex balloon, you know that over time, eventually that balloon shrivels up. You didn't do anything to it. The balloon was tied. What was happening is that when the rubber gets stretched, these teeny tiny holes occur. And over time, gas particles slowly escape through those teeny tiny holes, thus making your balloon shrivel up. That's the process called effusion. The final vocabulary word, diffusion, is the lower middle picture. And diffusion is something that you do experience in your everyday life. It's basically the mixing of gases. And it happens naturally. Some examples will be farts. All right, when you fart, where the area of the origination is, it's a very strong, pungent smell, and that smell eventually diffuses throughout the room, and other people start to smell it. Oh my God, gross! And eventually, over time, the smell goes away because those gas particles continue to move, and they just blend and mix in with the atmosphere of the room. Same thing when you open a bottle of perfume or you spray some perfume. Right where the source of the spray is, whoo, it's a really strong smell. Over time, other people are going to start to smell it because the gases will diffuse throughout the atmosphere. Thank you for listening to this lecture about the different properties of gases and how we can develop our gas laws about them and how they're related. And when we get together in class, we'll start to do some more of the math to help you calculate